Hey, everybody. Okay. Uh, so, having gone through all of that about stars and the components of our galaxy and the populations of stars in our galaxy, it was kind of a lot, right? But the reason to do all of that is so that we can now look at other galaxies and say, all right, what can we figure out? How can we use what we know about the lives and deaths and evolutions of stars in our galaxy, the neighborhoods and the structure of our galaxy? How can we use this to look at all the other galaxies and make heads or tails of what they look like? And this is super helpful because, in a lot of ways, every galaxy is a little bit different. Every galaxy is a little unique. And so, trying to make heads or tails of what's going on, we got to fall back on the basics of how things really work to anchor looking at all of these different galaxies, all these different objects, and say, well, okay, what do they have in common? How are they different? And how can we look at the big picture to figure out what's going on? So, what can we figure out about other galaxies beyond the Milky Way? Um, well, when you look at the two closest dwarf galaxies that we were looking at last time, the Small Magellanic Cloud and the Large Magellanic Cloud, what do you notice? Um, Look at them carefully. It looks like a pretty picture of something, but the nice thing is these are separate galaxies. They're not full-size galaxies like the Milky Way. They are dwarf galaxies, which means what? It means they're smaller than normal galaxies. And most dwarf galaxies you find most dwarf galaxies orbiting around large galaxies. Not all the time, but oftentimes. Um, Look at these things. What you notice is they don't have a nice regular shape. They don't have a nice orderly regular geometry the way our galaxy does, or the way M51 does in the last lecture. Um, are the stars here young or old? Well, how can you tell the age of a population of stars? Look at the color. If you have a big group of stars, look at the dominant color, and the color can tell you, or at least it can give you a handle on the age. Is this galaxy blue or red? And you'd say, well, there's these big blue areas, right? There's this big blue area over here. There's this big blue area over here. Okay, a blue population of stars is young or old? Young. And you could look at that from the last question I said. Oh, is it blue or is it red? And you go, but there's these big red areas, right? There's the big red stuff over here. There's the big red stuff over here. Okay, is that the whole population of stars, or is that one of those blotchy red H2 regions, one of those stellar nurseries? And you go, well, it doesn't look like the whole population of stars is red. It just looks like there's these little smaller, more isolated red areas. And that's the telltale sign that tells you, oh, okay, you're not looking at a red group of stars, you're looking at hot red gas. What gas gives off a lot of red light when you heat it up? It's hydrogen. So each of these red blotches is another one of those stellar nurseries, one of those H2 regions, because these two galaxies are undergoing a lot of star formation. For a galaxy this size, which is not that big, to have this giant H2 region and a few other decent sized ones over here and over here, there's a lot going on in this galaxy. There's a heck of a lot going on over here in the Tarantula Nebula, like we talked about last time. These two galaxies, the Magellanic Clouds, are what you call irregular galaxies. So there are three major types of galaxies. There are the spiral galaxies that we looked at last time. There are the irregular galaxies that we're looking at here. You can tell the type of a galaxy basically by looking at it. An irregular galaxy is one that doesn't have a nice, clear geometric structure. It's called irregular because it looks kind of lumpy and there's no pattern to the star formation. Where's the star formation in a spiral galaxy? It's in the disk, right? It's in the arms especially. So you can tell the difference. Both spiral galaxies and irregular galaxies have a lot of active star formation. How do you know? It's the red, blotchy H2 regions and a lot of blue stars. The difference is, in an irregular galaxy, the star formation is kind of happening all over the place. There's no clear pattern to where the star formation happens and where it doesn't. It's kind of random. Irregular galaxies also have a lot of gas. But of course they'd have to, right? Because you can't have star formation without gas. Irregular galaxies tend to be irregular because they're interacting with some other galaxy. That if you just let stars and galaxies off on their own, typically what will happen is the orbits of the stars will regularize, right? That stars will settle into a nice orderly orbit around the galaxy, and then you have a galaxy that has it'll end up having a more regular shape if you let the stars do that and the gas do that. Left of their own accord, a galaxy will tend to settle into a regular shape. So the reason why these galaxies are irregular, there must be something causing them to be irregular. There must be, in this case, the reason why the Magellanic Clouds are irregular is because they are orbiting and they're passing by a big galaxy like the Milky Way. And the gravity of the Milky Way is twisting them and stretching them out and causing the gas. So this galaxy is kind of stretching off in this direction. This galaxy has like a lobe of gas and new stars over here. Like there's a big cluster of blue young stars over there, totally dissociated from the main body of the galaxy. Why irregular galaxies are irregular is not always that easy. Irregular galaxies are sort of the miscellaneous category of galaxies. Does it have a nice regular geometry? No, throw it in the irregular galaxies bin. A lot of galaxies are irregular because they're interacting with another galaxy, and therefore the gravity is twisting them and changing the shape. Not always, though. We'll see some here in a minute. We'll see some galaxies that are irregular for different reasons. And that's really where the fun begins. It's really fun to look at some weird irregular galaxies and go, what's going on? Why? Why don't they look nice and orderly like the Milky Way does? So we'll see some of those in a minute. These are a couple of other dwarf galaxies near the Milky Way. Leo 1 here is a dwarf, what you call a dwarf elliptical. This is the third kind. There are three kinds of galaxies, like I said, spirals, ellipticals, and irregulars. And an elliptical galaxy is basically a big ball of stars. Or, well, in this case, it's a dwarf elliptical, so a smaller ball of stars. IC 1603 here is another dwarf irregular. Again, look at the populations of stars. What color do you notice mostly in Leo 1? It's more yellowish, right? So if it's a little reddish and, if the stars in Leo 1 are, orange and yellow, younger or older, it's going to be an older population. IC 1603 here is having a lot of active star formation. How do you know? Well, it's really irregular. There's a bunch of stars over here. There's a smattering of stars over here. You got like this vein of bright blue light going over here and a little bit more over there. There's no regular shape to it. It's not a spiral, and it's not a nice ball of stars like this elliptical. You can tell there's a lot of active star formation. How do you know there's active star formation in IC 1603? Well, if you've got star formation, what are you going to have? Young stars. If stars are being born, what are you going to have? Baby stars. What's the dominant color in a young population of stars? It's blue, and 1603 is very blue. once you get outside of the Milky Way and the dwarf ellipticals, or sorry, the dwarf galaxies, not all ellipticals, but the dwarf galaxies near the Milky Way, you can get out into the rest of, well, the universe. This is the Andromeda Galaxy. This is the serial number is M31. I think I may have said this earlier in the semester, but it's been a while. A lot of these galaxies have serial numbers, catalog numbers. They are items in a catalog of bodies in the universe. IC 1603, it means this galaxy is item 1603 in the IC. I think IC stands for International Catalog, something like that. M means it's an object in the Messier catalog, because Messier was a French comet hunter in the 1700s, I want to say. And Messier was looking for comets, and so he looked at all of these fuzzy glowing things that looked like maybe they might be comets, but they weren't comets. And they're not comets because they're not moving. So the Messier catalog is a bunch of fuzzy glowing things, which means galaxies, nebula, things like that. But they're not comets. So basically the Messier catalog is a catalog of objects that you might, he published this catalog thinking, hey, everybody looking for comets, look at those things. They're not comets. So don't be tricked. So item 31 in the Messier catalog is the Andromeda Galaxy. Andromeda is the next big galaxy over from the Milky Way. So all of these other galaxies that we've been talking about, all these other little ones, are in orbit or in the neighborhood of the Milky Way. Andromeda is 2.5 million light years away. It is about the same size, about the same mass as our galaxy. And it's also a spiral galaxy. So it's kind of the twin to the Milky Way in a lot of ways. Orbiting around M31, orbiting around the Andromeda Galaxy, is a bunch of other dwarfs also, a bunch of dwarf galaxies. The two brightest are these two dwarf ellipticals. And again, every galaxy looks a little bit different. And yet, you see the same patterns arise over and over again. The Milky Way and Andromeda, they have a lot in common. They got that bulge at the center, they've got the disk, they've got the arms of dust and star formation, much like the Milky Way. M32 and M110 are these dwarf ellipticals. What's an elliptical galaxy? It's an oval. It's an oval-shaped ball of stars. Sometimes the elliptical galaxy looks more round, more spherical. Sometimes they're more elongated and more oval-shaped, shall we say. But again, you see them over, you see these ellipticals, you see these dwarf ellipticals around Andromeda, much like Leo 1 that you find near the Milky Way. Totally different galaxies, and yet similar structures. Probably because they share a common origin, they share a common history. The other big galaxy near the Andromeda and Milky Way is the Triangulum galaxy, or M33. Triangulum, look at this. It is a spiral, right? You've got the bulge in the center, and you can see the spiral arms going in like this. And in the spiral arms, you see all those red smudges that tell you there's star formation happening in the spiral arms, just like in the Milky Way. So Triangulum is a spiral galaxy, and yet it looks different from the Milky Way and different from Andromeda. So they're all spirals, they're all spiral galaxies, but a little different. The Milky Way, Andromeda. So here's a map of our local corner of the universe. Here's the Milky Way and all the dwarfs orbiting around the Milky Way. Here's Andromeda and all the dwarfs around there. Here's the Pinwheel Galaxy is also another nickname for the Triangulum Galaxy. There's a few dwarfs around there. I said that most dwarf galaxies are orbiting around full-size galaxies, but not always, right? Like this one there, that one there. Those galaxies are kind of off on their own. So, okay. I said this is our own local corner of the universe. This neighborhood is what's called the local group. So the Milky Way, Andromeda, and Triangulum are the three full-size galaxies, the three major galaxies, along with a few dozen dwarf galaxies in our local group of galaxies. And the local group is about 10 million light years across. So 10 million light years is everything that's close to us. It's nearby in the universe. Let's pause here and let these numbers, because when you start, let these numbers sink in here for a second. When you start studying galaxies, the numbers get really big. You know how the first thing in the semester we talked about was like, oh yeah, in astronomy the numbers get real big real fast, and that's why you pick convenient units. Well, here it's kind of hard to get away from the fact that we're dealing with really big numbers, like the numbers of stars, right? In our little local group, there's a few dozen galaxies, but each of those galaxies has billions of stars, and they are millions of light years apart. The local group is 10 million light years across, which means it takes light, right? Light always travels at the speed of light. The speed of light is the fastest speed in the universe, and yet it takes light 10 million years to get from one end of the local group to the other. It takes 2.5 million years for light to get from the Milky Way to Andromeda, and from Andromeda to us. When you look at Andromeda, you're not seeing Andromeda the way it is right now. You're seeing Andromeda the way it was. If you go out tonight and look at the Andromeda Galaxy, which is hard to, it's visible to the naked eye, but you've got to really be in a nice dark sky. So if you want to see Andromeda with the naked eye, you got to really get out of town, someplace nice and dark in the desert to see it. But it is visible to the naked eye, just. But if you go out tonight and look at the Andromeda Galaxy, you're not looking at it the way it looks tonight. You're looking at it the way it looked 2.5 million years ago. The galaxy is 2.5 million light years away. So it takes light that long. It takes light 2.5 million years to travel 2.5 million light years. And so when we start looking at other galaxies, even the nearest galaxies, these are all nearby galaxies. The M31, the Andromeda and Triangulum are the nearest full-size galaxies, and yet we're always seeing those galaxies the way they were a few million years ago. And a few million years, in the grand scope of everything, a few million years is not that long. These are nearby galaxies. They're only, I say, tongue-in-cheek, those galaxies are only a few million light years away. That's close in this context. Every other galaxy in the universe is outside the local group. So when you look at M104, M74, when you look at all of these other galaxies, when you look at these gorgeous pictures from the Hubble Space Telescope or from other telescopes, you're looking at galaxies that are not in the local group. They are outside. They're farther away than 10 million light years. These are both spiral galaxies, right? Spiral galaxies, much like the Milky Way, but in ways slightly different, right? What do spiral galaxies have? Well, they all have a bulge of stars at the center, except not always the same size. Sometimes a spiral galaxy has a big bulge of stars in the center, and they're mostly bulged and have a small disk. So these are what are called bulge-dominated spiral galaxies. Sometimes a galaxy has a small bulge and a large disk. These are what are called disk-dominated galaxies. But again, similar structure. They've got a bulge, they've got a disk, they've got a halo. Hard to see in this picture, the halo usually is. So they've got the same structures, just with slightly different ratios. Some galaxies are massive enough, and some galaxies have so much of the mass concentrated toward the center that the gravity at the center of the galaxy wraps those arms tightly around it. So they're held really tightly. The spiral arms are held really tightly around the core. Triangulum is a disk-dominated galaxy, right? I wouldn't call Andromeda bulge-dominated the way M104 here is, but typically, and M104 is a good example, typically if you have a bulge-dominated galaxy, so much mass is concentrated at the center that you are going to have the spiral arms held really tightly. Triangulum, I think is fair to say, is a disk-dominated galaxy. It's not much bulge, it's mostly disk, and since the mass is more spread out, the gravity is not hugging the arms tightly around it, so the arms are allowed to spread out and are held more loosely as they orbit around the center of the galaxy. There are actually two kinds of spiral galaxies. So all of these ones that we've been looking at are normal spiral galaxies. And when I say, normal is not a fair word. I guess what you would call them is unbarred galaxies. Some spiral galaxies, the central bulge is not spherical, it's elongated into this bar. So basically, the bar in a galaxy, the bar in a spiral, it's more football shaped. It's more not quite lens shaped, but it is more football shaped. So this NGC 1300. Again, NGC is a different catalog, so it's number 1300 in the new general catalog is what NGC stands for. NGC 1300 is a barred spiral. So the bar in a barred spiral is that the central bulge is elongated into this bar. Whereas Andromeda and Triangulum, the bulge is spherical. It's round. And so you could call this an unbarred spiral. That's a good way to say it. Unbarred, barred. Here are some more barred spirals, right? So again, like when the center of the galaxy is stretched out into a linear bar, I think, so bar like an iron bar, I guess is what the image, what the name is conjuring, right? Here again, like the center is the center here is pretty round, except it's getting stretched out like that. And one of the cool things about barred spirals is that when you have this bar like this whole linear structure of stars and gas is rotating around the galaxy. And so what happens when you've got this bar rotating around like this is all of these stars rotating like this tend to stir up the gas at the ends of the bar. This is a great example, right? As the bar here is orbiting around counterclockwise, all of those stars and gas are running into all of this gas over here. And so it's jostling it, it's disturbing it. And so when you agitate that gas, you might be knocking the gas together, and that's going to cause the gas to become denser. And if the gas becomes denser, gravity is going to be stronger. The gravity will pull the gas into a collapse, and when the gas collapses, what do you get? Star formation. New stars are going to be born out of this agitated gas. And so in a lot of these barred spirals, you see this big spray of star formation flying off the ends of the bar because that bar is orbiting around, jiggling the gas. That gas, a few million years later, because again, these stars are all orbiting very slowly around the galaxy. But, after a million or 2 years, you end up with this spray of new stars flying off like this. And so you find that here too. like off the tips of the bar here, a spray of new stars going this way and this way. This one, because the bar is so small and as it orbits around it's triggering star formation, the stars here are kind of, the star formation here is happening in more of a ring, which is pretty interesting. Oh, pardon me. This is M109. This is probably the galaxy that looks most like the Milky Way, because it turns out, I've been saying this whole time, oh, we live in a spiral galaxy. Actually, it was a big discovery 10 or 12 years ago, that we actually live in a barred spiral galaxy. That that when you look through the dust and the gas, when you look toward the center of the galaxy, the picture that we saw in the last lecture, that big 360-degree survey of the whole sky in the infrared that lets you see through the gas to the center of the galaxy, it was when that picture was taken that everybody looked toward the center of the galaxy and they said, oh, it's kind of linear. The reason why it's not obvious is because we actually live in about this part of the galaxy. Our location in the galaxy is looking at the bar almost perfectly end on. So it's kind of like looking at a football, but looking at it down the long axis. And if you look at a football down the long axis, it looks round. It's only when you go slightly left or slightly right that you can tell, oh, there's some depth to it. It's not perfectly spherical. It's elongated. And so this is why it took so long. It took until just a few years ago for people to realize, oh, we actually live in a different kind of galaxy than what we thought. We knew for a long time that we lived in a spiral galaxy. Turns out we live in a barred spiral. So what? Who cares? Why is this a big deal? Well, because those bars can trigger a lot of star formation, like happening here, like happening here. Did this happen in our galaxy? Probably. If it's happening in all these other barred spirals, it seems likely, right? Maybe one of the reasons why our galaxy looks the way that it does. Maybe the reason why we have so many star-forming regions, maybe the reason why we have so many open clusters in our galaxy is because we live in a barred spiral. Maybe, and again, this is a big maybe. Take this with a big grain of salt, right? Maybe we wouldn't be here, right? Maybe our sun is one of those stars that was triggered to happen because barred spirals agitate gas and jostle it, cause it to collapse, trigger new star formation. Or maybe not. I mean, maybe that's not. Maybe we would still be here even if our galaxy was an unbarred spiral. That's a big if that I'm throwing around. But I think what is a fair statement is to say there wouldn't be nearly as many blue stars. There wouldn't be nearly as many young stars and active star formation in our galaxy if it were an unbarred spiral. I think that's a fair statement. Okay, so elliptical galaxies are the third major kind. So far, the only ellipticals that we've looked at are the dwarf ellipticals, but there are another kind of elliptical, and those are what are called the giant ellipticals. Giant ellipticals are the biggest galaxies in the universe. So I've got a picture. There we go. Okay, so here are a couple of dwarf ellipticals. These are those same dwarf ellipticals that are orbiting around Andromeda, right? M32 and M110. What do you notice? Well, it's a ball of stars. Sometimes that ball of stars is more round. Sometimes it's more oval shaped, more elliptical, hence the name. Do you see dust? Do you see dust lanes? No dark lanes? No. Do you see red blotches showing you that there's active star formation? No. You see any groups of blue stars, open clusters? No. Spiral galaxies and irregulars have lots of gas, lots of dust, and since there's gas, you can give birth to new stars out of that gas. So where you find gas and dust, you find active star formation, you find a young population of stars. Ellipticals don't have any of that. Ellipticals are just stars. There's very little, maybe not none, but there's very, very little gas and dust floating around those stars in these elliptical galaxies. And if there's no gas, there's going to be no gas collapsing to form new stars. And if no new stars are being born, you're not going to find young newborn stars. And therefore, you don't find ellipticals that are very blue, because you've got to be young to be blue. So the homework asks a question, so I'll say this, right? There are two subcategories of ellipticals. There are the elliptical ellipticals, which are the like round oval shaped ones, and then there are lenticular galaxies. Lenticular galaxies are the word lenticular literally means lens shaped, so they're shaped kind of like the lenses in your glasses if you wear glasses, which is that a lenticular galaxy, it has more of a disk, like a lens. It has more of a disk, so you might think, oh, that's a spiral, except a lenticular galaxy doesn't have gas and dust and star formation. So that's how you can tell a lenticular from a spiral, right? Lenticular and spiral galaxies are flatter, and they have a disk, but a lenticular doesn't have star formation or dust. Here's what I've been talking about. This is M87. This is one of those giant ellipticals. And when I say giant, I mean giant, right? Our galaxy probably has upwards of 1 trillion solar masses, 1 trillion with a T, 1 trillion solar masses. These giant ellipticals have dozens of times more than that, right? Our galaxy is like this size compared to a giant elliptical. These are the biggest galaxies in the universe. These are the kinds of galaxies that you find at the center of big galaxy clusters. Our cluster of galaxies, right, the local group of galaxies, we are living in a small galaxy cluster. Right? The local group just has like 3 major galaxies, a few dozen dwarf galaxies. That's not much. M87 is sitting at the center of the Virgo cluster, and the Virgo cluster has 1,000 galaxies, of which, like, again, here's the big daddy. These ones are more like the size of our galaxy, and then you've got some other galaxies that are all of these galaxies. Well, actually, that and that are probably foreground stars. That one. Gravity is the dominant force at these big distances, right? There's some serious mass in these clusters, and therefore gravity pulls these galaxies together into these clusters. And sometimes it's a small cluster like the local group, and sometimes it's a Virgo cluster, and sometimes gravity is so strong that it causes galaxies to crash into each other and become bigger galaxies. Well, imagine how many galaxies had to be eaten up to create a galaxy that size. Something that big compared to a galaxy at our size. Oops, like this one here. This galaxy has eaten a lot of material, a lot of stars to become that big. Okay, so here's a bunch of different irregular galaxies we're going to talk about for a minute. Not every irregular galaxy looks the same. Actually, in fact, no irregular galaxies look the same. Every galaxy is a little bit different. You've probably noticed this by now, right? Even when I say, oh, all these galaxies are spirals, yeah, but they all look a little different. Each galaxy, I mean, these are all elliptical galaxies, yeah, but they're a little different. Irregular galaxies all look very distinct, and the fun of this is to try to figure out. You got to do a little bit of detective work. Why are these galaxies so irregular? And these two galaxies are merging. You could probably bet that a while back, 10, 20, 50 million years ago, these were probably two spiral galaxies. but they're pulling each other together. And these two galaxies are whipping around each other. This one's going this way, this one's going that way. They are dancing around each other, orbiting around each other, and as they're tugging on each other with gravity, they're throwing gas and stars out. So they've got these tails. This is why they're called the mice, because they look like two mice with a big long tail. And eventually, these galaxies are going to dance around each other faster and faster and faster until they eventually collide and merge and become one big galaxy. Centaurus A on the left there is a giant elliptical, but wait, I just said ellipticals don't have dust. What's that big streak of dark stuff? That's definitely dust. So it looks like Centaurus A is a giant elliptical, but it's not. It doesn't fit the criterion. It doesn't match all the other ellipticals. So we're going to make it an irregular, because what this looks like is a giant elliptical that just ate a giant spiral. And when it ate that giant spiral, here's the disk of dust left floating around this elliptical galaxy. So if it, again, like I said, irregular galaxies are like they're the miscellaneous category. If you look at a galaxy, does it look like a spiral? Great, it's a spiral. Does it look like a barred spiral? Great, it's a barred spiral. Does it look like an irregular? Great, it's an irregular. That's right. Does it look like an elliptical? Yeah, great, it's an elliptical. If it doesn't neatly fit the pattern, if a galaxy doesn't neatly fit the pattern of spiral, barred spiral, elliptical, then you just say, okay, it's an irregular. So yeah, irregulars are sort of the grab bag. They're the miscellaneous of other galaxies. AM0644 is a ring galaxy, because the thing you can't see in this picture is there's a big galaxy up here, and the gravity of this big galaxy is pulling all these gas and stars up toward it. And as the gravity pulls the gas gets squeezed, it collapses, and it eventually, when it collapses, it forms stars. So you get this big ring of new stars orbiting around the galaxy as the interaction between these two galaxies triggers new star formation. M82 is totally different. If you look at M82 in the optical, what do you see? You'd go, oh, well, okay, so it looks kind of like a spiral, right? Here's the spiral disk, right? Because the spiral disk is where you find the blue young stars, except that in a normal spiral, you also find the dust in the disk. But the dust isn't here. The dust is going out like this. That's not what happens in a spiral, right? In a spiral, the blue stars and the star formation and the dust are all in the same plane. In this galaxy, the dust is going off this way. What's going on? Well, it turns out when you look at this galaxy in the X-rays, this galaxy is a starburst galaxy. Starburst galaxies are a name for galaxies that are undergoing massive star formation, right? Many times, they're forming many times more stars than our galaxy is. And that's why there's so many blue stars here, because there's so many young new stars. And apparently the star formation is still happening, because when you look in the X-rays, there is a fireworks display going off, right? Each of those hot spots is a supernova, because these are hot spots in the X-rays. What is hot enough to be giving off bright X-rays like that in such a confined space? It's supernovas. There are boom, 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 right? Each of those hotspots is a supernova. And so this galaxy has undergone a series of supernovas all in rapid succession. And there are so many supernovas happening all at the same time that when those supernovas explode, they're blowing out what? What gets blown out when a supernova happens? Gas and dust. And so many supernovas are happening around here all at the same time that all those supernovas are blowing all this gas and dust out this way. So this galaxy is irregular because it's a starburst galaxy. And so things are not happening. The star formation and the supernovas are in the disk, just like in a spiral galaxy, like you'd expect, but there's just so many There's so much star formation and so many high mass stars are being born. They live their lives, they die, they blow up as supernova so much faster than in a normal spiral. It's making this galaxy look irregular. In this case, it's irregular because the dust and the stars are going in different directions. So this is irregular for a different reason. Then you've got quasars. Quasars are galaxies that are emitting a lot of light because of that supermassive black hole at the center. Centaurus A is one of these. So here's Centaurus A in the visible spectrum. Here's a picture of it. Well, here's a picture of it in the visible overlaid with the radio. If you take a picture of this galaxy in the radio spectrum, there are two bright jets shooting out of the center of this galaxy, and it's blowing out a lot of hot gas, and that hot gas is giving off radio waves. It's blowing two big bubbles of hot gas out into space. The hot gas doesn't give off a lot of visible light, but it gives off plenty of radio, and this tends to stand out. Whatever is shooting those jets out is able to shoot out a jet of hot gas 100,000 light years out into space. What could be that powerful? It's a supermassive black hole. So quasars are another kind of irregular galaxy where in the center of these galaxies you have a supermassive black hole. And you might say, but wait, there's a supermassive black hole in the center of the Milky Way. The Milky Way is not a quasar, is it? No, it's not. And the reason is because our black hole, the black hole at the center of our galaxy, is quiet. Our black hole, what do I mean by quiet? I mean it's not feeding. There is some, every once in a while, some gas or a star will fall into the black hole in the center of our galaxy. But for the most part, our galaxy just has a black hole at its center, and that black hole is not doing much. It's just sitting there pulling stars into its orbit. These active galaxies, so there's a lot of different terms. There's a whole zoo of quasars. Sometimes they're called quasars. Sometimes they're called radio galaxies. Sometimes they're called Seyfert objects. There's a bunch of different names. When you get down to it, all of these things, what they have in common is that these are active galaxies. These have active galactic nuclei, is the term, AGN, active galactic nucleus. What do I mean? What could be active in the nucleus of a galaxy? It's the black hole. And so here's a bit of a cartoon. What you've got here is a supermassive black hole, meaning this black hole has millions or billions of solar masses, all in one black hole. And that black hole is feeding. There is hot gas falling in toward the black hole. This black hole, the stars get too close, the gas gets too close, the stars get ripped apart, and you have this accretion disk of superheated gas circling the drain, spiraling in toward the black hole. Again, just like when we talked about it before, you can't see a black hole, but there is so much gas falling into this black hole that the gas is being heated up to millions of Kelvin, and it glows in the X-rays and in the radio waves. I mean, it glows at all wavelengths. But the easiest way to see these active galactic nuclei are in the wavelengths that stand out the best. And so these are pictures in the radio spectrum, but also you get a lot of X-ray emission from these accretion disks also. So all of these hot spots there. You can kind of see it there, although it's hard to see it when it's superimposed on all the visible light too. So what you're seeing is the hot accretion disk as gas is about to fall into the black hole, but then this black hole has a strong magnetic field. And so this superheated gas, it's a plasma, it's a superheated gas, and it can get grabbed on, it can get grabbed by the magnetic field of the black hole, and it gets grabbed by the magnetic field and it sprays out the North Pole and the South Pole. much like the beams of a pulsar. It's very much like the beams of a pulsar, where the magnetic poles grab onto hot gas and shoot it out as two beams. And that's what you're seeing here, is these two beams, the North Pole and the South Pole, and I don't know which one's which, you can't really tell, but two jets of superheated gas flying away from the accretion disk of the black hole until eventually that gas slows down, and it's kind of like blowing smoke into the air, right? You blow the smoke until eventually the smoke slows down and it sort of accumulates and whips around like this. The gas, it's worth remembering, the gas is not escaping from the black hole because nothing can escape the black hole, right? This gas is escaping from the accretion disk before it falls into the event horizon, before it falls into the black hole. Because if it falls into the event horizon, it can't come out again. These active galactic nuclei, these supermassive black holes, are not uncommon. It looks like something like 10% of the supermassive black holes in galaxies are active at any given time. It's only active because gas is falling in, because it's accreting gas to it. The other 90% of the time, the black hole is asleep. And when I say asleep, I mean it's not feeding, right? But when that gas starts falling in and it starts heating up and then it starts shooting out as the jets, that's when the galaxy goes active. So a galaxy might not stay active all the time. It may only be active 10% of the time, and then it's after all the gas has fallen in or gotten shot out, there's no more gas to fall into the black hole goes quiet again, and then the other 90% of the time. So people have been studying this for several years, and I didn't grab a picture, but a few years ago, people were mapping the sky in the radio waves, and what they saw is these two big lobes, except they were really big because they're in our galaxy. Our galaxy, the Milky Way galaxy, actually has these two big lobes of radio emission north and south of the galactic plane. The black hole in the center of our galaxy is not feeding now, but it used to. That a while back, nobody's entirely sure when. I mean, I'm sure they've got some estimates, but a while back, there was a bunch of gas that fell into the black hole in our galaxy. Some of that gas got shot out as the jets of hot gas, and these two big lobes of hot gas are still out there, north and south of the galactic plane, shining with a little bit of radio emission and eventually cooling off. So the black hole in our galaxy is quiet now. These galaxies are active now, and if they run out of gas, then they'll stop being active. So these are really bright. I mean, these are some of the most, these are supermassive black holes with billions of solar masses gobbling up gas and becoming superheated. These kind of quasars can be seen from very large distances, especially if we are positioned, especially if our galaxy, especially if the sun, the Earth are positioned along the beamline, right? If we're looking at these quasars sideways, so the jets are shooting out this way, well, then you can still see them if you want to. But there are some quasars where the beam is pointed directly at us, and we might be right there. And so if our galaxy is positioned so that quasar is shooting the light and the gas straight at us, that makes that quasar much brighter, and therefore we can see it billions of light years away. Billions with a B. We can see some of these quasars, if they just so happen to be oriented at us nicely, we can see these quasars, these supermassive black holes, shining the flashlight right in our faces from billions of light years away. And that tells us a lot about the size, the distance, the age of the whole universe. And it tells us about the history of the universe. Because if you can look at something billions of light years away, you're looking at that galaxy the way it was billions of years ago, billions of years into the past. I talked before about studying galaxies is fun because they're attractive and, they all look a little different. But when you look at galaxies farther and farther away, you're looking at the universe further and further into the past. So you can learn about history. You can figure out the whole history of the universe. Not the whole history. You can figure out most of the history of the universe just by looking at it. You can look at a galaxy and say, what were galaxies like 10 billion years ago? All you got to do is look at a galaxy 10 billion light years away, and you'll know what the past was like. You don't just have to guess about the history of the universe. You can see it. If you can build a telescope that can see that far away, then you can see that far into the past. This is how we know how the universe got from the Big Bang to today, which is something we're going to get to in one of the remaining lectures. But before we get there, a little bit of practice. Here I'm going to show you some galaxies. What do you think the classification of that galaxy is? What kind of galaxy do you think M101 is here? Yeah, it's a spiral galaxy, right? Yep, round bulge, spiral arms, clearly spiral galaxy. How can you tell this galaxy has a lot of star formation? Well, when you have active star formation, you're giving birth to new stars. You're going to have young stars. How do you know if you're looking at young stars? There's a lot of blue stars. All those blue stars that you see in this picture have to be young because hot, blue, high mass stars don't live that long. So you must be looking at young stars. What about M81 here? What type of galaxy is that? This one's a barred spiral, right? Its central bulge is not round. It's elongated into this elongated oval shape. So this is a barred spiral. Yeah. Here's a tricky one. What do you think? That's a tough one, right? It's got dust, right? You can see the dust lane in there. So it has dust. If it has dust, you know it's not an elliptical. Is it irregular? Would you say this has a lumpy, random, irregular geometry? No. I mean, it's straight, right? It looks linear. Okay, it looks like it has a regular shape, so it's not D. It's not irregular. So if it's not C and it's not D, well, it's either a spiral or a barred spiral. And at that point, you may just have to agree to disagree. Because I'm sure if you got a room full of astronomers and said, is this a spiral or a barred spiral? People would argue around and around and around for an hour, and it's either A or B. I think that's the most confident I can come to given just this one picture. What do you think? If this is if this is a spiral galaxy, it doesn't look like a spiral. Where's the spiral? If this is a spiral galaxy, where is its disk? I'd say your best answer is A. The reason why this galaxy looks so straight and linear is because what we're doing is looking at the disk edge on. That is the disk, right? There's the bulge, and the rest of this is the disk. So it looks flat because we're looking at it so edge on. So A it is. How about this one? Yeah, this is one of those giant ellipticals. And when I say giant, I mean the picture here. This galaxy is so big, each of these dots, you'd think like, oh yeah, those are stars, right? No, each of these dots is a globular cluster with hundreds of thousands or a million stars. Each of them is a globular cluster. So that's how giant these giant ellipticals get. And you know it's elliptical because it's a round oval of stars and no gas, no dust, no active star formation. definitely see. Okay, so let's get a little bit more practice with this. Go ahead to the green book and work on the galaxy classification activity, starting on page 139. Should take you about 15 or 20 minutes, and you're going to look at some pictures of galaxies, and the pictures of the galaxies that you're looking at are the ones that are on the inside back cover of the book. I think the activity points that out to you, but just in case you're confused. All right, so go ahead, give yourself 15 or 20 minutes. If you can work with a partner, do it. And I've got one more thing to say. So after you're done with this, so pause the video. When you're done with this, press play again. All right? I'll pause right here. Okay. So the end of that tutorial asks a question about the Hubble tuning fork diagram. Like, what's going on here? And also the homework talks about this too. What is the Hubble tuning fork? Well, the Hubble tuning fork is sort of a diagram to help you break down the types of galaxies, the ellipticals, the spirals, the barred spirals, the lenticulars, and then, the irregulars just sort of thrown in there. Originally, Edwin Hubble, when he did this, again, this is about 100 years ago, when Hubble did this, he was trying to make like a rank, and when Hubble did this originally, it was just a straight line. It was from ellipticals on one end to spirals on the other. It wasn't until decades later that people started differentiating between the spirals and the barred spirals and split up this side of the graph into these two halves, into the spirals and the barred spirals. Why did Hubble do this? Why did Hubble list the galaxies like this? And the reason is because when Hubble, this is like 100 years ago, so this was with 100-year-old technology. When Hubble looked really far away at really distant galaxies, the only ones he could see were the ellipticals, the giant ellipticals. And if you're looking far away, when you're looking far away, you're also looking into the past, right? So in the past, if you see far away and all you see is elliptical galaxies, then you could draw the conclusion that, in the past, there were only ellipticals. And then when you look nearby, when you look in the nearby universe, you find lots of spirals. And if you're looking in the nearby universe, then it didn't take light that long to get here. So these must be galaxies that we're seeing these galaxies in the recent past, essentially in the present. So in the past, all you see is ellipticals. In the present, what you see is spirals. And so Hubble said, there must be an evolutionary sequence here. So Hubble created this tuning fork diagram, eventually became the tuning fork diagram, to imply, what Hubble was implying was that in the past you have ellipticals, and then ellipticals must evolve and turn into spirals. So you go from past to present, these turn into these. That's why you see these in the past and these in the present. There's a problem here. What kind of stars do you have in elliptical galaxies? You only have old stars, right? Ellipticals are much redder. They only have old stars because the ellipticals don't have gas and dust. And if you don't have gas and dust, you can't have active star formation. You can't have young blue stars. What do spiral galaxies have? Spiral galaxies have a lot of dust and gas. And if they have a lot of dust and gas, they have active star formation. They have young stars. So Hubble's idea that galaxies evolve from ellipticals into spirals, it sort of naively makes sense if all you're doing is looking at things in your telescope. But let's see if this makes any sense. How do you go from old stars and no gas, and then how does all of a sudden gas shows up, and then you have gas and young stars? How do you take old stars and no gas and turn that into young stars and lots of gas? Old things don't turn into young things. That's not how time works, right? Hubble had it wrong. ellipticals don't turn into spirals. You can't just all of a sudden, like, let an elliptical do its own thing, and after a few billion years, it suddenly grows spiral arms, and a bunch of gas shows up out of nowhere, and then new stars are being born. No, 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 no. That's not how that happens. Hubble was wrong. Why? Because he was using telescopes from 100 years ago. If you look nearby, if you look in the nearby universe, you see lots of spirals and lots of ellipticals and a bunch of irregulars. When you look really far away, when you look at the faraway galaxies, when you look very far into the past, all Hubble could see was the giant ellipticals. Why is that? Because they're giant ellipticals. They're really, really bright. They have insane luminosities, right? Hubble didn't take into consideration, or he did, but not enough. He didn't take a sufficient consideration to the fact that he can only see giant ellipticals far away. There are, now that we have better technology, now that we've got better telescopes and better cameras, we know that around those giant ellipticals, there's also a bunch of spirals and irregulars. You just can't see them if you've got, 1920s technology. And so today we still use this Hubble tuning fork diagram sort of as a way to just list the galaxies in no particular order, right? You just kind of, this diagram was originally created to imply that galaxies evolve from left to right. Today we know that's not what happens, right? Galaxies change because they collide with each other, right? Galaxies evolve not gradually over billions and billions of years. Galaxies change when they crash into each other, or when they whip around each other, or when they stretch each other out, and they become irregulars for a while until the stars settle back into a regular orbit, and then they turn back into regular spirals or ellipticals. So the tuning fork diagram is there today to just say, oh, okay, what does this look like? Oh, it looks like the other E3s. Okay, let's slot it into an E3. Oh, it looks like an E5. We'll slot it in there. But they don't evolve from one type into another on their own. They will evolve. Galaxies will evolve and change shape because of collisions, but not just because time happens. All right. So I just wanted to say that part because there's a couple of questions at the end of that tutorial that may not make perfect sense unless in a better universe where we would be there in class to talk about it in person. All right. So I hope that helped. I hope this is making some sense. Next thing we're going to do is we're going to zoom out some more and say, all right, so now that we've looked at a bunch of galaxies, what else can we tell about galaxies? What else can we learn about galaxies by observing them? And how can we take our observations of galaxies to zoom out and start looking at the universe, the large scale structure and history of the universe? That'll be the next big logo. That'll be the next big stop on our move toward the end of the semester. So I hope you're all doing well. Take care, and I'll see you on the other side. All right, bye.